Hey guys, my name is IBM and today I'm going to record lesson 4. This is going to be lesson 4 of quantum physics. I think in lesson 4 we are going to concentrate on the wave-particle duality and maybe the de Broglie wavelength. So this is lesson 4, Physics 9702, A-level paper 4. Okay, so let's introduce the wave-particle duality. So experiments have shown that light behaves as a wave because according to Young's double slit experiment and the diffraction grating that you saw in AS physics, light was behaving as a wave because light was showing interference and light was showing diffraction. Unfortunately, in lesson 2 and lesson 3, we saw experiments involving photoelectric emission or photoelectric effect. Another experiment that we were supposed to talk about is the Compton scattering experiment. Now, these two experiments show that a photon of light only interacts with a single photon of electron, and a photon of light with high enough energy displaces an electron from a metal surface. This experiment or such experiments indicate that light is behaving as a particle because we believe it is only particles that can displace other particles. Now, this leaves us in a dilemma, in some sort of dilemma. So, should we say electromagnetic radiation is a wave, or should we say electromagnetic radiation is a particle, or is behaving as particles? So, this is what leads us to the idea of the wave-particle duality. So, the photoelectric effect that we discussed above shows that electromagnetic radiation has or have particulate nature. In other words, the photons which make up electromagnetic radiations have particle-like properties. And if light waves can behave like particles, because we had already known that light is electromagnetic radiation and it was an electromagnetic wave. So if light that we already knew as waves can now behave as particles that we are going to call photons, perhaps why can't we also believe that moving particles can behave like waves? We already knew that light was a wave because it showed interference and diffraction. Then why can't we think if light which was a wave now behaves as a particle because of photoelectric effect and of course later on Compton scattering, then why can't we also believe that moving particles can behave like waves? This argument will be answered, or this argument will be brought to our understanding by what we shall call the de Broglie wavelength, or Louis de Broglie. So the photoelectric effect that we discussed above and the Compton effect, or called the Compton scattering, these have placed the particle theory of light on a firm experimental basis, that light behaves as a particle because it shows photoelectric effect and Compton scattering. On the other hand, the classical experiments of Thomas Young, and others, especially on interference and diffraction, show that the wave theory of light also rests on a firm experimental basis. So experiments confirm that light is a wave, such as interference and diffraction. Experiments still confirm that light is behaving as particles, such as photoelectric effect and Compton scattering. And now this leaves us in a dilemma. Should we consider light as a wave or light as a particle? I want you to recall that the characteristic properties of waves are that they show reflection, refraction, diffraction, and interference. Waves also do not have mass, or they do not have a charge. Some particles, of course, also show reflection. Some particles also show refraction. Some particles also do not have charge, just like light waves. So since particle models can also explain reflection and refraction, then it is only diffraction that we regard as the defining characteristic of waves. So we shall only consider diffraction as the defining characteristic of waves because particles can also show reflection. particles can also show refraction. If reflection is the bouncing back of light, then a particle can also bounce off a certain surface. If refraction is the change in speed, a particle can also change speed when it moves from one less dense media to a more dense media. But if a particle can show diffraction, because diffraction is the hardest property to be shown by particles, then if a particle can show diffraction, then we can conclude that it would be behaving as waves. So this now leaves us in a dilemma, which in fact we have to address. So in fact, if we can show diffraction, then we know that we are dealing with waves. As long as you can show diffraction, or if something can show diffraction, then it is behaving as a wave. So this has left us in a dilemma. Some experiments are showing that light behaves like a wave, while others indicate that it behaves like a stream of particles. And these two theories seem to be incompatible, yet both have been shown to have validity. So the theory that light has wave-like properties has enough evidence to back it up. The theory that light has particle-like properties has enough evidence to back it up. So these theories are not agreeing, yet both of them are valid and must be considered. So to solve the problem, famous physicists like Albert Einstein, Hertz, Louis de Broglie, they put their heads together and came up with a conclusion that this duality of light must be accepted as a fact of life. If light is behaving as a wave and there is evidence, if light is behaving as particles and there is evidence, then the scientists came together and just agreed that this coexistence of these two sides of light should be just accepted as a fact of life. So this is what we today call the wave-particle duality. The wave-particle duality. Duality coming from two or meaning two. It's like it's like we are accepting that light should have the wave-like properties and light should have the particle-like properties, and this is a fact of life. So these scientists agreed to solve that dilemma. The fact that light behaves as a wave and the fact that light behaves as a particle should just be naturally accepted as a fact of life. It's worth noting from what we mentioned in lesson 1 that the equation E equals to hf itself links the particle and wave properties of light. In this equation, we mentioned that E stands for the energy of the particle, which is the photon, yet F stands for the frequency, which is supposed to be the frequency of a wave. In summary, therefore, we can agree that light is a wave. And what makes light a wave? According to observations, light is a wave because light travels through space as a wave. The major evidence for this comes from diffraction, even though even interference is a good property to show that light is a wave. Of course, other properties such as light having frequency and wavelength, those are also properties which show that light is a wave. However, the major concrete evidence we can base on to conclude that light is a wave is diffraction, because diffraction is rarely showed by other particles. On the other hand, light also can behave as a particle. So we can think of light as a particle or being made up of particles because according to the photoelectric effect, light interacts with the matter as a particle, which we shall call the photon. The evidence for this is provided by photoelectric effect and even Compton scattering. So light also shows Compton scattering, that is when photons interact with a nucleus or when photons interact with an atom, they may knock out or they may give some energy to an electron, but because the energy is not enough to knock out the electron completely from the atom, the photon does not cease to exist. It just gives out some of its energy to the electron, which makes the atom or the electron in the atom just excited, so the photon will just have less amount of energy, and that's what we call Compton scattering. Maybe to demonstrate Compton scattering, so if I have an atom here and The atom has an electron. So a photon of energy comes to the electron, and it promotes the electron to, let's say, a higher energy level without it going out of the atom, without it being knocked out. So this photon now will scatter off with less energy. So if it had energy E1 when it is arriving towards the atom, now it has energy E2, and of course it has lost some energy. E2 is going to be less than E1 because it has given some energy to promote the electron to a higher energy state, which makes the atom to be excited. This idea here is what we call Compton scattering, and it is expected that this is only possible if light is interacting with the matter as a particle. So Compton effect, photoelectric effect and Compton scattering are concrete evidence that light has particle-like properties. So this is what we are going to call the wave-particle duality. Let's try to understand diffraction as a property which gives evidence, or diffraction as a property of waves. But this property is being shown by particles. Remember, we said if light is a wave and it has particle-like properties, then why can't we agree that moving particles should also have, or why can't we argue that some particles should also have wave-like properties? If light, that we already knew as a wave, has particle-like properties, then why can't we predict, or why can't we agree that things that we already knew as particles should also be having wave-like properties? So this takes us to what we call electron diffraction. Electron diffraction. Moving particles, as I've already mentioned, moving particles such as electrons also display diffraction patterns. Experiments with moving particles have shown that electrons show diffraction. But remember, diffraction is a property of waves. Electrons show diffraction, but remember, diffraction is a property of waves. Can we say electrons are waves? Remember, electrons are already known as particles. They have mass, they have charge. So, since earlier on things we knew as waves such as light had particle-like properties, then we are also seeing that things that we know as electrons, as long as they are moving particles such as electrons, they show diffraction. Experiments of this can be demonstrated in the laboratory using what we call a discharge tube, where electrons can be produced in the discharge tube, and when the electrons are produced in the discharge tube are passed through a narrow slit or a graphite film, they form what we call concentric rings, as shown by this diagram here. They form what we call concentric rings, and these concentric rings are called diffraction patterns. So inside this discharge tube, which is supposed to be in one of the scientific laboratories, if your laboratory has this, you are lucky, you can demonstrate this. So inside the discharge tube, we have an electron gun, which is the source of electrons. So of course, in the electron gun, you have a cathode and an anode. The electrons can be produced by thermionic emission, that is by heating the cathode. And when the cathode is heated and electrons are emitted, the electrons are accelerated by a very high potential difference between the cathode and the positive anode. So these electrons are directed towards a graphite film, graphite that is carbon. And when they go through the graphite film, they are projected onto the screen. And when we look at the screen, when we look at this screen here, inside the screen, this is what we see. We see concentric circles. And these concentric circles can become smaller and can become bigger depending on the PD between the cathode and the anode. So these concentric circles are believed to be diffraction patterns. When electrons pass through the graphite film, they undergo diffraction. And because of diffraction, they form concentric rings onto the screen, as demonstrated by this diagram. To fully observe this, you can try to follow this, to go visit this YouTube channel, and you try to watch the video of how electron diffraction occurs in the discharge tube. However, I want us to note that when electrons go through the graphite film or go through the graphite layer, which is extremely thin, they form what we call diffraction patterns, and the diffraction patterns are actually concentric rings. So a beam of accelerated electrons strike a layer of graphite, which is extremely thin, and a diffraction pattern consisting of rings is seen on the tube, as we have seen in the previous slide. So the concentric rings are actually diffraction patterns. The concentric rings are diffraction patterns, and do not forget diffraction is a property of waves. This therefore means that the electrons that we already knew as particles are exhibiting, or they are showing wave-like properties, or they are showing properties we would normally associate with waves. Electrons that we knew as particles, because they have mass, they have charge, are now undergoing diffraction. But diffraction is a property of waves. So electrons, which we knew as particles, are now showing properties of waves. If you recall your AS physics, for diffraction to be appreciable and maximum, the wavelength was almost the same as the size of the gap. For diffraction to be maximum, the wavelength was almost the same as the size of the gap. The wavelength of the wave was almost the size of the gap from AS physics. So, to observe diffraction, the wavelength of radiation should be comparable with the size of the aperture or the size of the gap. Recall that the separation or the interatomic spacing between atoms, the interatomic spacing is approximately of the order 10 to the power of minus 10 meters. You mentioned that in particle physics, AS physics. So this tries, of course, this can now tell you that perhaps the wavelength of electrons is approximately of the order 10 to the power of minus 10 meters, because for diffraction to occur, the wavelength is appreciably almost the same as the size of the gap. So if the interatomic spacing between atoms of graphite is approximately 10 to the power of minus 10 meters, then we can start predicting and thinking that the wavelength of electrons may be very close to 10 to the power of minus 10 meters. So the fact that diffraction is observed with electrons suggests that they have a wavelength of about the same magnitude as the spacing between layers of atoms. So the wavelength of electrons is approximately the same as the interatomic spacing between layers of atoms. So the atomic layers of carbon behave like a diffraction grating. If you recall diffraction grating, which was like a double slit but with many slits instead of only two. So the layers between the atoms of graphite are now behaving as if they are slits. And when the when the electrons go through these layers, they undergo diffraction. That's why we are seeing diffraction patterns onto the screen. Remember, diffraction is a property of waves, but now the electrons are showing diffraction. I want you to note therefore that electron diffraction, which we can also call electron microscope, because the electron microscope uses electron diffraction. Electron diffraction, or the existence of the electron microscope, is evidence of the wave nature of particles. Now we have evidence that some particles really behave as waves. Diffraction is the major property which cannot always be shown by anything which is not a wave. But if electrons can show diffraction, that's how we came up with an electron microscope. Then electron diffraction, or the electron microscope, is evidence of the wave nature of particles. Of course, we know that photoelectric effect, Compton scattering, is evidence of the particle nature of waves or of electromagnetic radiation. Now, electron diffraction or electron microscope is evidence of the wave nature of particles, because we have seen if light behaved as waves and at the same time as particles, then how about the things we knew as particles behaving as waves? And there is evidence that some particles behave as waves, as demonstrated by electron diffraction. So, when someone talks about the wave-particle duality, this is just an idea that light and matter, such as electrons, have both wave-like and particle-like properties depending on the circumstances. Waves or light and matter, such as electrons, have both wave-like properties and particle-like properties depending on circumstances. When I talk about light, light travels through space as a wave, and light interacts with matter as a particle. When I talk about electrons, electrons show diffraction, and diffraction is a property of waves. But already we knew that electrons were particles because they even have mass and they have charge. So, the wave-particle duality is simply the idea that light and matter, such as electrons, have both wave-like properties and particle-like properties depending on the circumstances. This now leads us to the idea of Louis de Broglie. This is what we're going to call the de Broglie wavelength. Remember we said if electrons undergo diffraction through a graphite layer, which is actually carbon, if electrons are undergoing through diffraction, yet the interatomic spacing is approximately 10 to the power of minus 10 meters, we say the wavelength of the electrons must be approximately or close to 10 to the power of minus 10 meters. This wavelength of electrons cannot be called just normal wavelength, but we shall call it the de Broglie wavelength. Around 1924, Louis de Broglie extended the idea of the wave-particle duality. His argument was that if light sometimes behaves as a wave and sometimes like a particle, then perhaps those things in nature that we thought to be particles, such as electrons and other material objects, may also have wave-like properties. We knew light as a wave, but sometimes it behaved as a particle. So de Broglie's argument was that why is it that we can't believe that those things that we knew as particles should also have wave-like properties, because those things we knew as waves have particle-like properties. And he proposed that the wavelength of a material particle would be related to its momentum in the same way as a photon. If a wave behaves as a particle, and therefore we can also believe that a particle behaves as a wave, then he suggested that the wavelength of a material particle would also be related to its momentum in the same way as a photon, in the same way as for a photon. Of course, Albert Einstein, using the special theory of relativity, had already shown that the momentum of a photon p. Albert Einstein already showed that the momentum of a photon p was equal to E over c, where E is the energy of the photon and c was the speed of the photon, or the speed of light. This was only relating to what we already knew as waves. But then Louis de Broglie is arguing that if what we knew as waves has particle-like properties, then why can't we believe that what we know as particles have wave-like properties? And if what we knew as waves have their momentum related to their energy by this expression here, then Louis de Broglie is arguing that the momentum of the particle should also be rated in the same way as that for a photon. So using P equals to E over C, and know that energy is hf over C, then, and of course we know that F is C over lambda, then it makes sense for us to say that momentum P is going to be equal to H, where there is F, I'm going to be put C over lambda divided by C. So that means the momentum is going to be H over lambda. So Louis de Broglie was suggesting if this equation applies to waves or photons acting as waves, then the same equation should apply to real material particles, because things we knew as waves are behaving as particles, then things we know as particles, some of them even are showing wave-like properties like electrons, then their momentum should be related in the same way as it is for the photon. Albert Einstein had already established the relationship between momentum of a photon with its energy using the special theory of relativity. So borrowing the same equation, P equals to E over C, then we derived P equals to H over lambda. And of course, if we make lambda the subject, we come up with what we call the de Broglie wavelength. So making lambda the subject, we have that lambda is going to be equal to H over P. Thus, for a particle having linear momentum, if a particle has momentum mv, because particles normally have mass, then it means we can write the equation lambda as h divided by mv. But of course, I can't use mv for a photon which has no mass. Therefore, the equation lambda equals to h over p is called the de Broglie wavelength. That equation is called the de Broglie wavelength. Unfortunately, if it is a particle, for it to have a wavelength, it must be moving, because P for a particle is equal to mass times velocity. So for a particle to have momentum, it must be having a speed. Therefore, we define the de Broglie wavelength as the wavelength associated with a moving particle. Any particle that is not moving will therefore not have a wavelength. If electrons were stationary, they would not be having electrons. They would not be having a wavelength. Any particle which has mass, for it to have a wavelength, it should be moving, and of course, it should be for it to undergo diffraction, most likely it should be moving at a very high speed. So the de Broglie wavelength is what we call the wavelength, or is the wavelength associated with a moving particle. The wavelength of a moving particle is the de Broglie wavelength. Okay, so that's what we call the wave-particle duality. Anything which has wave-like properties and has particle-like properties, then we can believe that it should also, anything which we knew as particle-like, anything we knew as particles should also have wave-like properties according to Louis de Broglie. And if that is true, then the relationship of their momentum with energy should be the same as that of a photon, which had already been established by Albert Einstein in his special theory of relativity. Okay, we qualified to do a few examples to concretize this or to understand this in more details. Of course, before you think about doing examples, I want you to notice that we have already seen an equation, or the most important equation to be using, that for particles, for moving particles, their momentum is going to be related to their energy by the same equation as the photon, and the energy of a photon is going to be E over C. Because a photon has energy as hf, this is hf over c, and remember f is equal to c divided by wavelength. And when you substitute for f, the momentum is going to be h over lambda, and this is the expression from which we obtain the de Broglie wavelength. Question number 1. Determine the wavelength of an electron that has been accelerated through a potential difference of 100 volts. So the potential difference is 100, or the accelerating speed is 100 volts, and it is an electron whose mass is known. So if it has been accelerated through that speed, it has kinetic energy. So it means the energy of the electron is EV, or the kinetic energy. The loss in kinetic, or it has been accelerated through a potential difference of this. So the gain in kinetic energy is going to be a EV. So I'll say E a half m v squared, that is kinetic energy, is going to be E times V, where V is the accelerating PD. So this means when I make V the subject, so this implies that V is going to be equal to the square root of twice EV, capital V, divided by the mass. Twice capital V divided by the mass. So we want to determine the wavelength. So you can find, no, I don't want to use that because I know some little mathematics. I'll just combine these two equations directly. So I know that momentum is mass times velocity. So when I combine these two, I'll of course multiply this side by 2. So I have mv. I'm multiplying both sides by 2 mv. So on the left hand side, I have 2m times a half mv squared equals to 2m times ev. So 2 was cancelled. So I have that m squared v squared equals to twice m e times v, capital V. So this is momentum squared. If you have noticed that, that is momentum squared. That is momentum squared. And remember also that momentum is equal to h over lambda. So it means momentum squared equals to twice me times v. And of course, momentum squared equals to twice mev. And also remember that momentum is equal to h over wavelength. So it means because I want to find the wavelength is going to be h divided by the momentum. So it means the wavelength is going to be equal to h divided by the square root of p, which is the square root of twice me times v. So I'll just substitute this. So the wavelength is going to be equal to 6.63 times 10 to the power of minus 34. That's of course Planck's constant divided by the square root of 2 times the mass, which is 9.11 times 10 to the power of minus 31, then times E, which is 1.6 times 10 to the power of minus 19, then times V, which is 100. So I just wanted to use mathematics to combine the two equations, and I just come up with a simple equation and I substitute at once. Alternatively, you can first calculate V by using this equation here. You get the speed. Then of course you can find the momentum by using this equation here. And then by using this equation here, you can find the wavelength, the de Broglie wavelength. But all those steps, that is wastage of time. So when I press my calculator, so I'll start from the denominators, 2 times 9.11 exponent minus 31 times 1.6 exponent minus 19 times 100 root of the answer. Then I have 6.63 exponent minus 34 divided by the answer. So this is giving me 1.23 times 10 to the power of minus 10. So that is going to be the de Broglie wavelength associated with a moving particle. Okay, so just to understand this, compare this with the interatomic spacing. So the wavelength of the electrons, or the wavelength is on the order of 10 to the power of minus 10 meters. That's what we have got. The wavelength of the electrons is of the order 10 to the power of minus 10 meters. So electrons can have wavelengths on that order, 10 to the power of minus 10 meters, and even smaller. What does that mean? Electrons can easily show diffraction effect because their de Broglie wavelength is similar to the spacing between the atomic layers. The reason as to why electrons will show diffraction is because their wavelength is comparable. Their wavelength is comparable or is of the same size as the interatomic spacing. Their wavelength is the same size as the spacing between the atomic layers. For diffraction to be maximum, the wavelength should be comparable with the size of the gap. So later experiments showed that protons, neutrons, and other particles which had a very small mass and could move at a very high speed all have wave-like properties. In other words, they all showed a diffraction. So experiments later on showed protons could show diffraction, neutrons could show diffraction, and other particles all did have wave-like properties. Okay, example number 2. So these are try examples. Normally I ask my students to just pick a calculator and tell me the answers, but I'll try to give a hint so that people get used to using the equation. So I calculate the de Broglie wavelength of an electron traveling with a speed of 1 times 10 to the power of minus 1 times 10 to the power of 7 meters per second. So de Broglie wavelength is equal to h divided by the momentum, or the momentum is h over wavelength, and this is going to be h divided by mass times velocity. This is going to be 6.6. They said we should use 6.6, but it's normally 6.63 times 10 to the power of minus 34 for Planck's constant. The mass of an electron is 9.1 times 10 to the power of minus 31. Then this small v is for the speed, which is 1 times 10 to the power of 7. I'll just check the calculator. So this answer is approximately correct. Calculate the de Broglie wavelength of an electron traveling with a speed of 5.5 times 10 to the power of 10 meters per second. So they have given us h, they have given us the Planck's constant. This is similar to the same question there. I'll just press my calculator so that you can check with your answer. 6.6 exponent minus 34 divided by 9.1 exponent minus 31 and 5.5 exponent 7. So I expect you to get 1.32 times 10 to the power of minus 11 meters. Calculate the de Broglie wavelength of an electron which has been accelerated from rest through a potential difference of 100 volts. Planck constant is given as 6.6. The mass of the electron is given as that. The charge is 1.6. So they want us to calculate the de Broglie wavelength. Okay, in the previous example, we saw that the de Broglie wavelength is h divided by momentum. And we also saw that momentum squared was equal to twice me times the accelerating PD. So momentum is equal to the square root of that. So this is going to be equal to h divided by the square root of 2me times v. Because they have not given us the speed, then you have to combine the kinetic energy of the electron, which is a half m v squared, to be equal to E times the accelerating PD. Then you modify this equation to come to that, as I did in the previous example. So when I substitute here, I will have 6.6. I always don't want to substitute 6.6 because I know it is supposed to be 6.63, which is given the list of constants, divided by the square root of 2 times the mass of the electron, which is given as 9.1 times 10 to the power of minus 31, times the charge of the electron, 1.6 times 10 to the power of minus 19. You don't need to put there the minus. Then times the accelerating field, which is 100. I'll just check with my calculator. 2 times 9.1 exponent minus 31 times 1.6 exponent minus 19 times 100, square root of the answer, 6.6 exponent minus 34 divided by the answer. This is similar to the equation I did in example 1, which is 1.22 times 10 to the power of minus 10 meters. So that is the de Broglie wavelength. Calculate the speed of a neutron with a de Broglie wavelength of 1.5 times 10 to the power of minus 10 meters. Planck's constant 6.6, mass of a neutron 1.7. Okay, I'll use the same space on this page. So we know that the de Broglie wavelength is equal to h divided by the momentum. So they have given us the de Broglie wavelength. We have h. We want to calculate the speed, and this is the same as h divided by mass times v, which means that the speed v is the same as h divided by mass times wavelength. So I've made v the subject, so they said we should use 6.6 times 10 to the power of minus 34. The mass is 1.7 times 10 to the power of minus 27. The wavelength is 1.5 times 10 to the power of minus 10. So this is 6.6 exponent minus 34 divided by 1.7 exponent minus 27 divided by 1.5 exponent minus 10. So this is approximately 2.6 times 10 to the power of 3 meters per second. Calculate the de Broglie wavelength of a 10-gram bullet traveling with a speed of 300 meters per second. So remember, the Broglie wavelength is equal to h over momentum, which is going to be h divided by m times v, mass times velocity. So this is going to be h, which is 6.63 times 10 to the power of minus 34 divided by the mass is 10 times 10 to the power of minus 3 to change it to kilograms times the speed, which is 300. Sorry, yes, 300. So 6.63 exponent minus 34 divided by 300 times 10 exponent minus 3. So this answer is correct. Of course, you notice that this is a very small de Broglie wavelength. We cannot have such a space for diffraction to occur. So this bullet may not undergo diffraction. So using the same formula, you can check this one, you can check that one. I can't check all of them. Calculate the de Broglie wavelength of a 0.2 kilogram ball moving with a speed of 15 meters per second. So de Broglie wavelength equals to h divided by momentum, which is h divided by mv, which is going to be 6.63 times 10 to the power of minus 34. The mass is 0.2 and the speed is 15 meters per second. So this answer is correct from my calculator. However, I want you to observe that this wavelength is extremely small. We cannot have such interatomic spacing, or we cannot have such a gap for diffraction to occur. So diffraction may not be observed with such a spacing. So this is a wavelength. This wavelength is unimaginably small. Indeed, the wavelength of any ordinary object is too small to be measured and detected. This wavelength of 10 to the power of minus 4 is too small, so it cannot be measured or even detected. The problem is that the properties of waves, such as interference and diffraction, are significant only when the size of the slit or the size of the gap is not much larger than the wavelength. These two should be comparable or comparably equal. And there are no known objects or slits to diffract waves only 10 to the power of minus 34 meters long. So the wave properties of ordinary objects will go undetected. So because the wavelength is unimaginably small, we cannot have such a slit or such a gap for diffraction to occur. That means the wave properties for big objects or for most known objects are actually not detected. But of course, we can agree that tiny elementary particles such as electrons, as we have seen, they are also matter. They are also particles, and these ones have showed diffraction because of their wavelength. So, since the mass of such particles, such as electrons, is in the denominator and is very small, a very small mass should have a larger wavelength. So the particle should be extremely small, should have an extremely small mass, and also should be moving um, at a high speed. So since the mass m appears in the denominator of the equation, lambda is equal to h over p, which is h over mv, a very small mass should have a much larger wavelength. A very small mass will have a much larger wavelength. That's why the wavelength of electrons is about 10 to the power of 10, I mean minus 10. That is relatively large enough. Okay, what is the wavelength of a person of mass 65 kilograms running at a speed of 3 meters per second? So by calculation, the wavelength is going to be equal to h divided by m times v, which is going to be 6.63 times 10 to the power of minus 34 divided by the mass is 65 kilograms and is running at a speed of 3 meters per second. So from my calculator, 6.63. So from my calculator, this is a correct wavelength and is running through an opening of width 0.8 meters. Notice that the wavelength is much smaller than the opening of the width. Therefore, the person will not undergo diffraction. So this wavelength is very small indeed compared with the size of the gap. Hence, no diffraction effects would be observed. People cannot show diffraction. People cannot be diffracted through everyday gaps because the de Broglie wavelength of these people is much smaller than any gap that a person is likely to try to squeeze it through. So we don't expect a person to undergo diffraction, yet according to Louis de Broglie, he's suggesting that things we knew as particles should also have wave-like properties. But human beings or people will not show diffraction because their de Broglie wavelength is much smaller, is much smaller than the everyday gaps. Therefore, they can't undergo diffraction. So for this reason, we do not use the wave model to describe the behavior of people. We get much better results by regarding people as large particles. So I can't use the wave model and I transfer it to people, but I can use it to other particles such as electrons, protons, those particles which have extremely small masses. Okay. If an electron and a proton travel the same speed, which has the shorter wavelength. So of course, from the equation lambda equals to h over mv, they have the same speed. So v is the same for both. Now it depends on the mass. So which has the shorter wavelength? The one which has a bigger mass has a shorter wavelength. And of course, a proton has a bigger mass, so it has a shorter wavelength. Okay. So if an electron and a proton travel at the same speed, the proton has a shorter wavelength because we notice that the wavelength is inversely proportional to the mass if the speed is the same, because h is a constant. So since the equation, lambda equals to h over mv, and the mass of the proton is about 1040 times the mass of an electron. The mass of a proton is around 1.67 times 10 to the power of minus 27. Yet the mass of an electron is about 9.11 times 10 to the power of minus 31 kilograms. So the mass of a proton is about 1840 times greater than the mass of the electron. When they have the same speed, then the wavelength of the proton is going to be 1840 times smaller than that of the electron. So the wavelength will have a shorter wavelength. The proton will have a shorter wavelength. Why do we say that light has wave properties, and why do we say that light has particle properties? Of course, we say that light has wave properties because we see it act like a wave when it is diffracted, and we say that light has particle properties because we see it act like particle because it shows photoelectric effect and Compton scattering. So for wave properties, we shall concentrate on diffraction or diffraction, and for particle properties, we shall concentrate on photoelectric effect and Compton scattering. So Compton scattering and a photoelectric effect show the particle nature of light, or the particle nature of electromagnetic waves. Okay. X-rays are used to find out the spacings of atomic planes in crystalline materials. Describe how beams of electrons could be used for the same purpose. So X-rays are used to find out about the spacings of atoms in the planes of atomic planes in crystalline materials. Describe how beams of electrons could be used for the same purpose. So how would we use electrons? And how might electron diffraction be used to identify the sample of a metal? Okay, so of course we know that electrons can behave as waves, so they can be diffracted by spaces between atoms, as simple as that. Because electrons can undergo diffraction between the spaces of atoms, then they can be used for the same purpose of studying atomic structures. Because electrons undergo diffraction, because their de Broglie wavelength is comparable to the interatomic spacing, then they can also be used to study crystalline structures. Then how might electron diffraction be used to identify a sample of a metal? So each metal has a different lattice structure, so each will produce a different diffraction pattern. Different metals have different lattice structures. So when electrons undergo diffraction, they will produce different diffraction patterns. Therefore, we can easily distinguish the different metals. So the idea of electron diffraction can be used to study crystalline structures because electrons have the same de Broglie wavelength as the interatomic spacing, but different metals will have different lattice structures, so they will also produce different diffraction patterns when electrons undergo diffraction. And that's how And that's how we can use electron diffraction to identify a sample of a metal. You deserve a self-check. Explain what is meant by de Broglie wavelength. That one is the wavelength associated with a moving particle. I think that one is direct. I will not talk about it. The diagram shows the principles of an electron tube used to demonstrate electron diffraction. Calculate the kinetic energy in joules of the electrons incident on the graphite film. Of course, we know that kinetic energy, Ek, is a half mv squared, which is the same as the charge of the electrons times the accelerating PdV. The accelerating PD is 5 kilovolts. So you should be able to calculate that. So you can just use E times V. Show that the momentum of the electrons is equal to 2Ek times m. So if kinetic energy Ek is a half mv squared, so it means twice Ek is equal to mv squared. I multiply both sides by m. Twice m Ek is equal to m times m, which is m squared v squared. So this means twice m Ek is equal to momentum squared. So the momentum is going to be the square root of twice m times Ek. Calculate the de Broglie wavelength of the electrons. Of course, the de Broglie wavelength is equal to h over momentum, which is h over the square root of twice m times Ek. Because you have kinetic energy in the first in the Roman 1, you just use kinetic energy in that equation. I think that is a good hint. Discuss how the wavelengths of neutrons and electrons moving with the same energy would compare. So wavelength is equal to h over twice m times kinetic energy under the square root. They have the same kinetic energy, but the mass of the neutrons is greater than the mass of the electrons. In other words, the mass of the neutrons is about 1840 times bigger than the mass of the electrons. So since wavelength is inversely proportional, then it means the wavelength of the neutrons will be smaller than the wavelength of the electrons, because the neutrons have more mass than the electrons. So the wavelength for the neutrons will be, because the neutrons have more mass, the wavelength will be less. Will be less than the wavelength for the electrons. Okay. So you can attempt most of these questions. As a particle travels faster, does its de Broglie wavelength decrease, increase, or remain the same? You just look at the equation. Lambda is equal to h divided by mv. So if v increases, lambda decreases. Beam of an electron is accelerated from rest through a period of 1 kilovolts. What is the energy of each electron in the beam? So energy is going to be kinetic energy, which is going to be E times V. Calculate the speed, then you now equate a half mv squared to that energy. Calculate the de Broglie wavelength. The de Broglie wavelength is now going to be h divided by momentum, which is actually h divided by the square root of twice m times kinetic energy, as we have seen in the previous example. Would you expect the beam to be significantly diffracted by a metal film in which the atoms are separated by a spacing of 0.25 times 10 to the power of minus 9 meters? So it will depend on the wavelength. If the wavelength is of the order 10 to the power of minus 9 meters, or very close to 10 to the power of minus 9 meters, then you will conclude that the beam is diffracted. If the wavelength is far away, or not even comparative, not even close to 10 to the power of minus 9 meters, then you can't say it is going to undergo diffraction. Diffraction is only possible if the wavelength is comparative to the size of the gap. Diffraction is only possible if the wavelength and the size of the gap or the atomic spacing is almost the same. Okay. Explain what is meant by wave-particle duality. Remember we said wave-particle duality is just the idea that light and matter such as electrons have both wave-like properties and particle-like properties. A beam of electrons accelerated from rest through a speed of 1 kilovolt. What is the energy? We have this is a repeated equation, I think. Capture the speed, capture the de Broglie wavelength. Would you expect the beam to be significantly diffracted by a metal film in which the atoms are separated by a spacing of 10 to the power of minus 10 meters? Diffraction is only possible if the wavelength is comparable or is of the same size as the atomic spacing. If the wavelength, the de Broglie wavelength that you have obtained, which is actually this one, is comparable to 10 to the power of minus 10, then this is going to be possible. So you see 10 to the power of minus 11 is not very far away from 10 to the power of minus 10. So the de Broglie wavelength is almost of the same order as the separation between the atoms, so diffraction is possible. Okay, I think I've exhausted everything I wanted to say about the wave-particle duality and the de Broglie wavelength. Do not forget the momentum of a photon is given as energy divided by c, which is hf divided by c, which is hc over c times lambda, because f is c over lambda, which is h over wavelength. And that is the wave-particle duality and the de Broglie wavelength. Until next time, bye-bye.
Myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Something from nothing. I sit here looking for an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as you. Something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life changes, just open the door. One thing's certain, I'll always be